guess we should start, right?
Yeah, Noreen talked to Roy, and he'll intervene a bit later, so if you're okay, we can start with him. He said he's fine. So I guess Harris has been working here for some time.
I guess everyone pretty much knows him, so.
Yeah. And he was, he's one of the mainframes of Orbit in many ways. He has built a lot of the infrastructure in Orbit together with Ivan, especially the mobile part of Orbit. Ivan has contributed quite a bit to his thesis and his work, giving ideas on what to do. I helped him out with some of it, and three of you helped him out quite a bit, so thank you very much. He has started his postdoc at Princeton Advanced School. Well, sort of with a moon shot.
Is Vince involved in that work at all?
I know for one postdoc who's collaborating with Moog and Vince Poole on social networks.
It's formally not a yet postdoc, or he has to finish here.
Yeah. Right.
Thank you.
So yeah, let me start with the slide, which is kind of an overview what we tried to do in this work. And that's basically to look at the spatial and temporal coherence of the V2V channel. The idea, in simple words, being if I put, say, multiple antennas on a car roof, whether I can improve V2V communications in any sense. Or, for instance, since it's pretty easy to flip between space and time, if I have a single antenna system and I perhaps want to employ time diversity, which means basically to repeat transmissions, what's the time scale on which I should do these things? Whether it's a symbol, is it on a time scale of symbols or packets or whatever. So what the thesis is about, it's about V2V propagation, and then we basically worked first on a simpler problem where we have a wireless link and we have a single reflector which creates channel perturbation in the channel. And for that, we performed experimental study in two different unlicensed bands at 2.4 and 5 gigahertz with the stationary and the moving vehicle. And what we did there, we basically tried to model how the channel transfer function and the power changes as something in the geometry changes. And there's only basically three objects. There's a reflector, a car which is passing nearby the link, and then there are transmitter and the receiver. For a multiple reflectors case, we based on what we learned from the first item, from the first study, we tried to apply that to a numerical analysis where we add a bit more challenging environment where we have more reflectors, mainly cars passing by and houses. And for that, we only perform numerical analysis in a 22 megahertz band. So for that case, we are trying to estimate what's the coherence distance and coherence time from simulated channel transfer functions. The common theme of both of these is the idea that we have to deal with the short-range links, short-range propagation modeling, where these huge typically metallic objects are packed into a small, relatively small area. So you have to do something to deal with that, and the way we did it is basically to slice up the reflectors into small square tiles. Then we modeled radar cross-section of each of the tiles, and then we, based on that, calculate channel transfer function. We are trying to figure out how the channel looks like, model the channel. So the outline of the talk, that was more like outline of the dissertation. The outline of the talk is there's an introductory part, which I'll try to show some motivation slides why do we care about this problem, and mainly why we spend so much time on a single car reflector geometry, which looks kind of weird. You know, why do you care about a single car? You want to do this magnificent experiment where you go on Route 1 and measure for half an hour as 2 million cars passing by. Then the presentation will go into the second part where we talk about the single car reflector case study, and then the third part is about multiple reflectors. So going to the first part, to the introduction, there's been quite a lot of excitement about vehicular networks, and basically there's three groups of applications. One is road safety, and that one is probably more challenging with respect to stringent delay constraints and to reliability. Then there's information and road assistance, and finally there's entertainment. So they are kind of lined up by importance. There's a lot of standardization effort, a lot of emerging protocols. There's this TSRC protocol, how do they call it, group of protocols, which include Wave 802.11p. The propagation, the environment itself is quite interesting. First of all, this short range issue where you have a lot of these reflectors packed closely together. They create reflections, so they create multipath. In some situations, they can obstruct the link, so you have line of sight versus non-line of sight. And of course, since they usually move, then practically always you get time varying channels. But the issue is, so now, what is the time scale, for instance, of time variations? Can we track these variations or not, or do we have to do something to deal with these variations? Are they very fast or very slow, or what do we need to do? So here's an example of what people are trying to do with V2V networks. This is General Motors a couple of years back. So what they do, all of these cars, they using wireless network, they exchange information about their speeds and positions. And let's suppose that the car in front wants to change the lane. He might have the guy on the right side in the blind spot. And then since the network is, since they exchange information about about the positions, his safety system can illuminate the side mirror. The point being that the car on the right side might not be visible in the mirror, but there's a illumination which can blink and say, yeah, you have to be careful, there's actually someone hiding behind you, which on Route 1 people do all the time. And then I like this example in particular because there's this nice geometry, this position of cars, which we'll see many times in this presentation. So let me try to convince you that it's actually a very common situation. So for instance, you can have this case, as we've seen before, where a car passes two communicating vehicles. Then you might have this case, which is kind of a congested road, and parking lots are pretty much the same. Only there are probably less movements in that case. And then this is a case that Larry studied some time ago. Suppose you have a receiver which wants to download a lot of information from a roadside unit. Let's say it's entertainment, they want to watch the movie. So a convenient time to do that is when you're stopped at the traffic light, because then you probably have a line of sight link. This is so-called Winlap's so-called info stations concept, where you basically utilize these nice propagation conditions to quickly download a lot of data. But at the same time, maybe as you're waiting to make a turn or even to go straight, there are many cars passing, and again this nice geometry, transmitter, receiver, and the reflector repeats. So now going to these experiments with the single car reflector, we'll first talk about the reflector tiling in RCS, and then we'll show experimental results. So first thing I want to point out is that this issue of short-range propagation. Conventionally, for instance, in cellular systems, you assume that, for instance, mobile terminal is in the far field, and then you, when you're modeling channels, plane wave approximation holds, which means you're far enough from the antenna to observe the wave front. As the waves progress from the antenna, they don't appear as spherical, but rather as flat. And that's a nice thing because, for instance, another nice, because then you don't care about phase change in space. Basically, you can assume when the wave hits, say, an obstacle, the phase is the same at all points on the obstacle, right? And then another really convenient thing is that you can say when you're far away from the antenna, for relatively small areas, for relatively small distances, you can neglect the wave, the amplitude decay. You can assume that the amplitude of the waves is constant, which leads to the famous Clark's model, right? Which says basically there's this relatively small area in which the phase really matters, and the phase, waves of the approximately same amplitude but different phases add up together, and then the channel ends up messy, being messy. So one way to deal with unlike this case, to deal with short range, and first way to do that is basically to solve difficult method of moments integrals numerically, which is problematic because you might end up these numerical methods. The drawback is that you have to have a lot of computations. Typically, you slice up the surface over which you're integrating into very small elementary surfaces, which have to be much smaller than the wavelength, which basically means much smaller, typically means 10 times. So per area of squared wavelength, you might have 100 of these elementary surfaces, which means when you transform this into matrix form, it's humongous. So our approach is, our trick, what to do is basically to introduce these tiles, which are slightly larger. They're typically, turns out that they're typically on the order of half of the wavelength, and that's where you gain in comparison to method of moments. So this is actually how tiling approximation looks like. You look at the if you look at the illuminated side of the car, one that's exposed to the radiation from the transmitter, what you do basically, you chop up its silhouette into small tiles. Now, to determine the right size of the tiles, you use far field conditions. So the idea is now to make the tiles sufficiently small so that the reflection from each of the tile at the receiver appears as a plane wave. Basically, the receiver is in the far field of every tile. And then the way to do this, you have to use more stringent conditions. The common far field conditions, which you usually find in the textbooks, turns out not to be good enough. So, but the approach has certain limitations. First, if you have a very high frequency or very short wavelength, then this is the expression that kills you. If lambda is small, then delta has to be very small as well. So it's pretty much not applicable for very high frequencies. And then for very low frequencies, there's a third far field condition which says the distances have to be larger than the wavelength. And then in a vehicular environment on a road, that's pretty much hard to satisfy. Let's say by an order of magnitude.
Hard not to satisfy.
No, what I mean
No
is.
It's always more than a foot away.
Yeah. Pretty much. That's how much space you have between the lanes. So okay. So, but then the issue is how much power is reflected. The issue is how much power is reflected from a tile, and to answer that question, that's modeled through the radar cross section. One way to do that is a combination of physical optics and stationary phase approach, which basically leads to this idea that you take this complex body, this curved, shaped with certain curve, and then you look at these particular points on that surface, which have this nice property that they bisect. When you form angle between this point and the transmitter and the receiver, they bisect. Their normal bisects this angle, which means that tangential plane in that point, the tangential plane in that point is orthogonal, right? Would be orthogonal on this plane, incidence plane, where the transmitter, receiver, and the specular point are. And then basically that leads to a simplification of integrals, which describes scattering. So the good property of this approach is that it's applicable both to the dielectrics and conductors, unlike the I'm trying to avoid actually showing it, but there's this formula with the sync terms, which models also applying physical optics. You model radar cross-section, but only for ideal conductors. So our problem here is that if we want to apply this approach, we might not be able to find a specular point on a flat surface, right? Because it's when the surface is curved, you might actually hit some of these, even more than one of these specular points. If it's flat, it might be oriented in a way that there's no specular point. It's interesting to note that there's kind of similar work where this German group, what they did, they basically took, and that's quite interesting, they took Ford Focus, which is, I guess, small car, but it's interesting because I'm driving one. So they took this car and they put the whole car into the anechoic chamber, and they measured its RCS. And then from these measurements, they went to this optimization procedure where they said, okay, we are going to limit the number of scattering points. We are going to say maybe there's 10 or 12 of them. And these are going to be not the real scattering points, specular points, but rather virtual points. So we are trying to, we are going to try to find the best points on the car, which when we apply numerical analysis result in field, scattering field, which or radar cross section which is close to the measurements. So then, as I said, the question is, so the problem is the flat tile might not have a specular point. So in order to overcome this, what we do in our case, and we call this radar cross-section bisecting most of the time, bisection or something like that. What we do basically, we first tilt the tile. We project it by this angle var theta, and then when it's tilted so that it coincides with the tangential plane, then we basically apply a simple physical optics approximation to the radar cross-section, which is basically this part cosine beta times. This is quite common formula, and this part comes from the projection. So now the question is, how good is that? Turns out it's surprisingly it's actually not very accurate, because in a way it's an abuse of physical optics. You are supposed to apply physical optics for electrically large surfaces, electrically large plates. That's typically something on the order with the diameter maybe at least 2, usually 3 lambda, 3 wavelengths. And our conditions typically force the size of the plates to be less than that, maybe on the order of half lambda. And when you look at the compare our radar cross section and the sync one with the sync formula that works only for metallic for conductors, with the method of moment solution, there's a pretty huge gap. But surprisingly, when you go into experiments and apply this to the modeling, it gets both of these give decent results, give decent agreement with the channel power measurements. So now, from the radar cross section, that's actually an ingredient to figure out what's the power of the wave that hits the receiver and that's bounced from a particular tile, given a certain transmit power, distances, and antenna gains. And then the phase is reconstructed from the distances relative to the wavelength, and there's a term which depends on polarization. For instance, if your tile is ideally conducting, or if you can assume that's ideally conducting, then basically this term is either 0 or pi depending on polarization. So then from the tile reflection power and phase, you reconstruct the channel transfer function. Basically, at n discrete tones, you add a line of sight term, you add the ground reflection, and you add the sum across all the tiles with the amplitude and the phase of these reflection terms from the previous slide.
Does the tile orientation in your formulation influence the phase?
I think it does, because it affects the Fresnel's coefficient. Yeah, so for non-ideally conducting materials, this will be the function of angles phi r and phi t as well.
But suppose it's ideal. If it's ideal.
Here, if it's ideal dielectric.
No, ideal conductor, sorry.
Oh, if it's ideal conductor, then it boils down to 0 or pi. I don't have it in slides. I might have it in some older presentation, but when you actually let me see if I can find it.
No. I did not mean to detract you from the flow.
That's okay.
I guess the short version of the comment: if you had 2 tiles joined like this, so the person who doesn't know about tiling would say, I don't see any, I just see one bigger surface. Then you'd say that acts as a mirror, bigger tile. And then if you sort of break it slightly, then another person would say, well, they're not in phase anymore because of this tilt. So maybe model deterministic or stochastic, that's a different matter. So I was just curious. It looks like you make no distinction. So all all tiles in phase unless it's some part of the car which is sort of like a Jaguar, it's curved, so it's further away. So,
yeah, when I'm comparing the model to the experimental results, I'm actually assuming that the illuminated side is flat. I'm not taking it because that was much simpler.
Okay.
That was much simpler. It was very hard for me to. I had these mechanical drawings from some book. It's very hard to map that into real distances.
Okay.
So it turns out that the channel transfer function actually converges to a certain solution as the tiles shrink. And after you hit a certain tile size, which depends on the far field conditions, there's no further point in reducing tiles. You always get the same model, the same prediction for the transfer function. So basically, what happens here for this particular geometry, tile size 20 centimeter and 10 centimeter doesn't satisfy the far field conditions we previously seen. And once you hit that numerical boundary, after that you always get as you reducing tile size, it just increases computational burden. Burden gives the same answer. So now let me go to the experimental model validation, where we did two groups of experiments. First with the stationary vehicle. That's convenient because it enables to quite precisely or sufficiently precisely measure the geometry, distances, disposition between the objects, with the idea being that you want to study small changes on the in the geometry on the order of inch, because the phase is what really matters, and phase changes a lot with an inch distance, and that's what creates fading. So to accurately measure geometry, it must not change. So it's easier to fix the vehicle, do the measurements, then perturb something else, and repeat the measurements and so on. But then you also want to try whether the model works with the moving vehicle, and then again, due to the method we applied to measure the channel, you have to have slowly moving vehicle because we use the vector network analyzer. But then you cannot do anything better than using the model, trying to estimate the car trajectory to see if the model gives reasonable description of what a car was doing while you were recording the channel. So, and we did this in two bands, and as a metric to compare the model and the measurements, we used the channel model. So here's the setup. The most important piece is, of course, the vector network analyzer, which is the instrument which sweeps a certain band at n discrete tones. It basically sends a sinusoid on the transmitting antenna. The receiving antenna receives it. It's boosted by the amplifier. But then the point is the transmitter and the receiver are in the same box. So they can exchange phase information. And so the box can figure out not only how much the amplitude changed, but also how much the phase changes as well. And so the point being that it gives you complex numbers, complex channel, full channel transfer function. And we spent quite a lot of time automating it, and it's probably the most interesting to me and most exciting part of the work. So there's quite a lot of trade-offs with this experimental setup with the VNA. So for instance, all the transmitter and the receiver must be connected with the cables. So that means that they must be practically stationary, So you have to move something else in the environment in order to create channel perturbations. But on the other hand, the good thing is that now that you have the complex channel transfer function, for instance, it's easy to go to time domain and back to frequency domain. It becomes trivial. Now, another problem you have when you apply VNA is the frequency resolution versus coherence time. So if you want a very high frequency resolution, a lot of samples in a certain band, the instrument takes some time to measure. In the meantime, the channel can change. And I'm pretty certain that there's people in MILAB who use this, after I was done, who use this setup, and I'm not clear whether they actually paid attention to this, or maybe they didn't care. Maybe the averaging was fine with them. So the idea is not to violate, to do sweep fast enough, or to do as little as possible samples in frequency domain, as little as possible tones, not to violate the coherence time. And then, of course, this parking lot behind MILAB is nice because it's undisturbed site, but of course, one can claim, but that's not a realistic highway. But for this initial study, that's exactly what you want. So basically, what the instrument does is it reconstructs the channel transfer function from the scatter parameter S21, which is the ratio between the received wave and transmitted wave that goes into the two-port network, where in our case this two-port network is a wireless channel. And then, so here's where you want to go into time domain and correct use this property of use this nice feature of complex transfer function. You go into time domain, and then you figure out, so this huge parking lot, empty space, if the car is at certain distance, then when you look at the impulse response, in time domain it corresponds to the certain distances, meaning that whatever you see that you receive after a certain time cannot be from your setup, from the objects that you care about, and the objects actually being an object, the car. Everything else that's coming later after a certain threshold basically is coming from the background. These are buildings surrounding the parking lot, maybe reflection from the ground. Well, reflection from the ground you cannot probably remove this way, but walls, then foliage around it, then you can clean up that pretty well. Then there's a lot of limitations on mobility. Since the instrument can be very slow, the question is then you have to perform the sweep inside of the coherence time, and if you roughly estimate the coherence time as the inverse of the Doppler shift, that can help you calculate how fast can you drive your car. And it turns out that you're good if you're driving roughly 3 meters per second. You'll be below the blue line, which is what you want. It's kind of barely satisfied, but I think it's sufficient. So then
it's the advantage of driving it slower.
Right. I guess the only disadvantage would be that it takes forever to do the experiment. Because this way, to do one circle around the antennas takes 30 seconds. So, and then if you want to do, 10 trials, it just takes a lot of time, right? So your point is good, actually. That's the first part, when you actually park the car and do everything stationary is fine. So the most important bullet in this slide would be that you want to pay attention to so-called intermediate frequency bandwidth, which is, So now you have, the instrument has this receiver, and that receiver, as it moves from tone to tone, has a certain bandwidth, and you can control it. It's controllable, I believe, from 10 hertz to 100 kilohertz. But if you narrow it to 10 hertz, say to 10 hertz, the advantage is now you're improving your SNR according to the KTB formula. But then the problem with it is that going to time domain, the impulse response of your setup is very long. So it will take a lot more time to perform the sweep. So again, you have a trade-off, right? You want to have some intermediate frequency bandwidth, which is small, which is smaller but not too small. And then, of course, it better be large enough to accommodate the Doppler. So if there's a Doppler shift, it better be fitting into the frequency response of your receiver. Otherwise, you're not measuring the power correctly. So this is the graph test of how much the channel changes when nothing moves, and basically across a minute, every 6 seconds you do a sweep. The sweep lasts maybe 100 or 200 milliseconds, but you repeat it every 6 seconds 10 times, and this is what you get. So to give you perspective on the scale, this is 1 dB. So in a minute, maybe swings by 0.1 dB. So now, going to these experiments with the static vehicle, the way you do it, it's pretty hard to move a vehicle precisely with some inch distance. So you rather want to park the car, park it on a few different positions, and then each time you fix the car at a certain position, you move the antennas. You move the receive antenna, and you do that by moving it an inch by an inch in 2 directions. And then what you do, you want to compare, you digitize the car, right? You this illuminated side of the car, you slice it up into tiles. You model the channel transfer functions, calculate the powers. So now you want to compare these powers to the measured channel powers, and basically you form a prediction in some area which is maybe 30 by 30 inches. And the reason why you do that, first of all, the model has certain errors and certain approximations, like for instance that the side of the car is assumed to be flat and it's actually not. And then you cannot measure the distances so precisely, maybe you're a few inches off, so you want to accommodate that. So then what you do, you're trying to fit your measurements to the predicted power by doing exhaustive search through the area of model powers. And you're basically trying to guess, trying to guess actually what's the actual position of the receiver with respect to the car and the transmitter, rather than what you think it is. So then here are sample results. So this is the predicted power, and these are the measurements, and this is how they fit. So the blue line is our bisect approximation to the tile radar cross section, and the green line is the sync formula that works only for conducting materials. And this is kind of typical or slightly less than typical. You usually get better accuracy than this with respect to the position. So then going to the experiments with the moving vehicle, what you do there is you put pylons on the parking lot, you put antennas approximately at the same position where they were in the previous experiment, and then you start at this point and drive around the pylons. And so this is a kind of qualitatively what you get. So if you perform the experiment without the car completely removed from the site, and you let the instrument run in 30 seconds, there's pretty much nothing moving, so you don't see any variations in time, and you see some channel selectivity. These are reflections that are coming from walls and the trees around. And then when the car is actually passing the antennas, then when it's exactly between the antennas, then you see a lot of change. And this figure basically presents this figure only averaged in frequency, so this is actually power rather than the channel transfer function magnitude. And depending on antenna patterns, you can see quite a lot of change in channel, maybe on the order of 10 dB as the car passes the antennas. So now, again, you go into this data fitting procedure, where what you do, you again calculate channel powers at all the positions where car might be. So between the pylons and the antennas, you take into account car width, right? So the car illuminated side cannot be here, only in this area. And you calculate this matrix of powers, and now you're trying to so you take the measurements, you guess a certain initial starting point, because you don't know where the car actually hit when and where exactly the car hit this feasible area, right? So you're trying to guess that, and then you're trying to progress through the matrix of predicted powers by going forward with the same speed with which the car goes, and you allow for the car to go to bit shape, wiggle left and right for a very small delta, let's say 1 centimeter. And so it's kind of dynamic programming search, right? And then what that gives you is something like this. So the blue line is the measured power, and the black line is the prediction. And this is the guess of how the car traversed, how the car passed the antennas. So these small shifts to the left and to the right, they really matter. They dramatically improve the agreement between these two.
Does the car, in the model, does the car orientation change, or
it's moving only forward. Still, I'm not sure I can handle it. Maybe suspension.
I'm just curious. So when you correct the trajectory and you find that's a good step, what you do? Did you just shift the car over?
Yeah. I'm not taking into account the angle.
Okay.
So I'm just moving it parallelly. I guess it's a very small distance, so the angle is actually very small. It's easier to just do parallel shift, which is unrealistic.
That's pretty sober, right?
Pretty sober driving. I guess his projection angle doesn't change.
Yeah. So now, going to the third part, the numerical study with the multiple reflectors. The idea is now to form a number of propagation geometries. But first we consider this case where the transmitter broadcasts messages to the trailing vehicles. And we form 8 line-of-sight geometries where the receiver is immediately behind the transmitter, and 8 geometries where there's a, say, large vehicle between the transmitter and the receiver. And that's kind of similar to an old Lee's experiment, which had the same goal, to figure out what's the coherence distance, how much you should separate antennas on a base station to achieve a certain diversity level. The propagation geometries include 2 types of scatterers. There's a car model, which is modeled as a conductive flat plate 4 by 0.8 meters, which is slightly elevated above the ground, which is kind of what most sedans are. And I have somewhere in the draft there's a table which actually shows that, for instance, Ford Focus kind of in all his incarnations kind of fits this. It also fits the Mercedes as well. And surprisingly so, I was once we were doing these experiments, Ivan and I, and he tried his Mazda, and then I figured out his Mazda actually looks like a big car, but it actually has a lot of plastics. So metallic surface is pretty much the same. So it's kind of
real glass that makes a difference.
I guess I
No,
didn't.
This car is it's a lot of window glass.
Yeah.
Even though it's a bigger.
And it turns out that I tried modeling this without the glass, and all these results are without the glass, just taking into account metallic parts, it worked pretty well. And then, so the houses are then flat plates, say 15 by 4 meters. I don't know if this is an upscale neighborhood or what kind of neighborhood it is. Let's say that there's in between the houses there's maybe 10-meter space, and I'm assuming that they're basically pure dielectrics with some permittivity, which is reasonable number for these constructing materials like bricks and mortar. And then this array of houses is uniformly distributed with respect to the curve. There's a certain distance between the houses and the road. So the idea is then that the reason why we looked at suburban residential road, because it's the simplest to perform, the easiest for the numerical analysis, because the cars are close enough, and then it takes less time to actually perform simulations. So the idea is that on the average, the vehicles on the road are separated by, say, 22 meters, which is kind of minimum safe distance that corresponds to the speed of 40 kilometers per hour. So in this model, we perturb the vehicle positions. We assume that this is 2D Gaussian, and these Gaussians independent in direction of travel and perpendicular to it, but we don't allow collisions. We don't look into this case where the cars might go out of the lane boundaries. So there's a huge part of this numerical analysis is how to model what the car does on the road, and we try to do it in the simplest way. So then we create 8 of these, let's say, line of sight geometries. So the car is then modeled as basically initially as a box which is 4 by 1.8 meters, and then the distance varies 22 plus minus something, so it turns out to be 8 to 36 meters. And there are cars that are passing from the other direction, and then this convoy of cars is thrown randomly, and then the houses are also thrown randomly in the longitudinal direction, and then uniformly distributed with respect to the curve. And then similar for non-line of sight, only in this case there might be some bozo with the big truck who actually obstructs the road. So then, as I said, the car is modeled as a box, and what really matters is the illuminated side of the car, which is just a rectangle 4 by 0.8 meters. And then looking at the car heights, 1.5 meter for antenna height looked like a reasonable number. And then the idea is you can throw this antenna randomly wherever you like on the car roof, which is assumed to be 2 by 1 meter, which is slightly larger, slightly longer than the typical sedan roof. but it's a nice rounded number. So then now you go into this numerical analysis step by step. So first you calculate the transfer function for all feasible receiver positions, which is the same formula we've seen a long time ago for the single reflector. It's only just more terms added to it, more reflectors. Then since this is Larry's big contribution, there's this issue with the transfer functions being non-stationary. Basically, it's sufficient just to look at the mean. The mean varies a lot across all these possible receiver positions. So to deal with that, you split the receiver area into smaller squares. And inside of each of these smaller squares, you basically assume stationarity. And then you correlate transfer functions, but only inside the squares. And then on top of that, you form the statistics across the squares. The statistics on the correlation coefficient. And from that correlation coefficient, you actually you can figure out what's the coherence time and distance of the channel. You basically look at the distance or time at which it drops below a given threshold, the threshold typically being 0.5. So now, to calculate the transfer functions, with the 2.5 centimeter resolution, which is like 5 samples per wavelength, but it's better than what Nyquist in spatial domain would require, right? You calculate transfer function, you calculate channel response at 89 tones inside 22 megahertz. And then for non-line of sight geometries, you simply discard a line of sight and ground reflection. You're only taking into account the reflectors that are on the sides, which means that the diffraction, let me go back, the diffraction from the obstacle is neglected, which is kind of
I said you usually use first deflection in your models.
Yeah, we already discussed it with Harry.
yeah.
It's going to be an next project.
Next project.
Okay, so the spatial correlation coefficient you obtain by, and Larry nicely put it together, by basically correlating across frequencies. So you take a frequency response, correlate across these 22 megahertz, and you end up with the correlation coefficient given two positions of the receiver and given a certain one of these geometries, 16 geometries. So then you go into this procedure. We can call it smoothing, I guess, as well. So what you do, since you now assume stationarity inside of the squares, you can say, well, my correlation coefficient inside of each of these smaller squares depends only on the distance between the points and not where the actual points are. And now you do some averaging. Basically what you do, first you look only into 4 particular directions. So direction of travel perpendicular to that and 2 diagonals. And then you take all the samples of a certain distance, let's say 2.5 centimeter in particular direction, and you average correlation coefficient for all these. So to give you an example, for instance, let's say that this smaller square is meter by meter. Since the resolution is 2.5 centimeters, you have 40 points you have 40 rows and so 40 rows, and in each row you can have 39 of these samples of the correlation coefficient. So overall you do averaging over 1,560 samples for this particular distance. So now, as you increase the distance between x1 and x2, the number of samples reduces. So finally, you end up with only 40 samples, one sample per row for the largest distance. And it's even more complicated for diagonals, so that I don't want to even go into that. There's a then square root of 2 term, and it gets really messy. So now, here are some sample results. It turns out, although if you now do the statistics, so you end up having for each separation between the points, for each distance, you end up having a single value for the correlation coefficient in one of the boxes. So if the boxes were 1 by 1 meter, that means in 2 by 16 meters, you end up with 32 values. And if you take smaller boxes, you'll get more values. And that's what we also tested. We tried these squares of 0.25 centimeter and 0.25 meters and 0.5 meters. And we wanted to compare how the variance across these squares changes. And it turns out it's basically the same. It doesn't matter how big the square is, which is really nice and kind of surprising. You'd expect if I take twice as more samples, my variance should drop. My standard deviation should drop by, say, 3 dB. But surprisingly, this doesn't happen. Somehow, the fact that reducing the square size and increasing the number of squares, on the other side reduces the number of samples inside of the square. And since they are kind of bound together, that probably results in variance that doesn't change with respect to the number of squares. But of course, for instance, for line of sight, turns out that the model predicts a heavily correlated channel, and even for non-line of sight in the most cases, and this is in the direction of travel, the variance is of course larger, but it still remains, let's say, 0.8.
So why do you think this you have such a high covariance correlation?
I have a slide. If you wait maybe three more slides, I'll show you the colors. That might give some answer. So now looking at the directions, it turns out that it really doesn't matter in which direction you're trying to move. So whether you're moving in the direction of travel, perpendicularly or in one of these diagonal directions, you kind of get the same results. So the orientation of the antennas doesn't matter. So then, when you look across 8 of these geometries, and I'm trying to highlight the examples that we've already seen, line of sight 5 and line of sight 7, they are kind of all nice, they are showing pretty much the same thing. They don't change much, except for maybe 1 or 2 geometries for the non-line of sight case, which kind of resemble what you would want to see if you want to apply diversity techniques, right? There's a drop below, say, 0.5 at maybe 3 wavelengths, which is like maybe 35 centimeters. So that means for this particular geometry, if I were to have antennas which are separated by 0.3, 0.4 meters, that would give me some benefit.
So what are you really measuring here? What is this rho? Essentially.
Conceptually,
Whether you might get some benefit from diversity antennas, basically. The lower the correlation, the higher the potential benefit.
Right. Rho is what? The difference, essentially the distance between two
rho is
channel.
How far apart the antennas are.
I missed it. Here.
you're looking at how from these 2 points you're taking 2 channel transfer functions, right?
Right.
And then you're trying to find how much they
Differ.
they change by moving. Right?
Yeah.
And if they don't change, then you're not
That's-
happy.
And you're not happy or you are happy?
Well, it depends.
From a diversity
Right.
standpoint, I'd say you're not happy.
Yeah.
If one fades, then the other one's likely to fade also.
Yeah, then putting multiple antennas doesn't buy you anything.
But the question is why, is because that often happens when the channel is very good. So
Yeah, so then you're fine, then you don't need
nothing to
diversity in the
complain.
first
Right,
place.
if you're a diversity salesman,
And you're.
Yeah, yeah.
But
That's exactly the point of the powers. When you see the powers, that's exactly the case. You don't need
So how,
that.
I guess the variation depends on how fast the car would be going.
Yeah, in time domain, yes.
So.
This is kind of more of the case where I say, I'm going to freeze the time, and I'm going to assume that antennas at a particular position, and to see how much channel differs at these two positions. If I were to actually answer to the question specifically about the coherence time, I can do, and what I'm doing is simple calculation. I say, let's say the car moves with a constant speed, so I can map the distance to time. But I believe that's kind of an upper bound on coherence time, because in reality, if you have a, say, single antenna system, and you want to see how much the channel is going to change while you move a certain distance, in the meantime, the other reflectors are moving as well. So kind of on the average, you should see more perturbed channel than just simply, measuring at a particular time at 2 points. I don't know if I managed to lose you all with this.
But when you measure your row, right, you choose S specific S, right, and then X1 and X2 are 2 positions at a certain distance, right?
Right.
Maybe what Roy is asking is, okay, if you take your box, right, and then your box is, remind me how big is it?
Let's say 1 by 1 meter.
1 by 1 meter. But what if the antenna? I mean, I know that you did this boxing for stationarity reasons.
But also
What if the antennas are on 2 different, they're like much more than 1 meter
yeah,
apart?
but there's also this practicality issue. The roof is, let's say you want to put antennas on the roof. There's a certain size.
My car has quite a bit of
Maybe 2 by 1 meter.
maybe more than 2 meters.
2 square meters.
You have a big sun comes out.
So in some sense, if you're looking at how different are these channel transfer functions from this place to this place, you would have to look at further distances. And
Yeah.
also, like, this just like if you do cross correlation normalized by the energy, the waveform can be the same, but the energy of the whole waveform can be much less.
Yeah.
Your roof is clear, isn't it? You have a moon roof in your car, it's glass.
I have a moon roof here.
Paris' car is sun, so it's just metal. Sure.
X cars.
X. Well, 22 years of service. That's respectful.
is that illegal?
There you go.
Anyways, I guess.
Yes.
So Harris, like if
So
you did this experiment, and you recreated this situation, and you have that picture of the houses and the cars, and you left the houses out, would anything be substantially different?
Yes, I think so. Houses are probably more important than the cars because they are so huge. They are so huge. So in this case, I'm assuming they are 4 by 15 meters, something like that.
Yeah, but they're 15 to 15,
Then they are a bit farther away.
Farther away, yeah. So when so that's one question. The other question, of course, is the opposite. You get rid of the houses and you leave the cars and the road.
Yeah, I didn't look into that.
Well,
what's
so if you
the
have to
significance?
speculate qualitatively, what would you expect it to be?
I think still the houses are more important because the cars might if they are not very close to the antennas, in between the antennas, they're on a very shallow angle, and then the radar cross section is really small, so they don't affect the radar cross section much. Then the houses, since they are farther away, but also makes their contribution significant, is then that the angles are not so huge, right? And then the radar cross section is larger. So I think houses are probably more important than the cars. Unless you have a car which is literally sitting on next to the antenna.
That is interesting. I mean, you can show that.
Yeah, I have a few backup slides. Let me.
But those angles are important. I never thought about it. The better angle, is diagram.
Yeah, so this is, for instance, this line of sight case situation, right? This is actually the mean receiver position. So the receiver combs this area, right? This is where the transmitter is. Two cars. This car really doesn't matter. It's really too far, and the angle is really sharp. But the houses are these four probably are what creates the propagation environment. And that's probably why it doesn't perturb much. There's only these four houses and nothing else. And then this is when you average the simulations and calculate the power, this is what you get. This is probably the how do they call it, beating from the two-wave propagation, ground and line of sight. And then another one, typical non-line of sight example, where you have the obstructing vehicle, and then you have maybe two cars, and the distance is larger, so the mean power is lower, and then you have these houses around. But for some reason, this geometry doesn't give much fluctuations in power unless the receiver is in this particular area. But keep in mind that the receiver also dances according to this Gaussian distribution, so it's most likely to be here, where the channel doesn't change much. So finally, we can take a look at why.
So would the changes be even smaller if for instance, you said, oh, actually, there are many places on the turnpike or the front where now they have these barriers that are 25 feet tall, and they have 2 miles of barriers. So then you would, if you had the barrier rather than the houses, you'd have even less fluctuation.
I think there would be more fluctuations, because then you have, simply speaking, more tiles. So there's more rays coming at the receiver. That should probably create more diversity, more diverse channel power. In this particular case, you actually have quite a lot of.
To my mind, you move a little bit, it's the same set of reflectors over and over again.
Over and over again. That's pretty dull.
Or
I'm afraid I had some constraints with timing yet, so I tried to do it the simplest way. The point of
second year intuition. You got 2 flat walls.
I would not say I have intuition on this, but if you have intuition, I'm glad to.
Yeah, if you open your eyes in one spot versus the other, you can't tell the difference of how it's going. That's important.
Yeah.
That's pretty profound.
So
what happened with the line of sight 3? Why is it special?
non-line of sight 3.
Yeah.
I don't know. I couldn't figure out anything other than that.
Sorry, I missed. What was this? Frequency low power?
It goes down. Power is much lower.
Yeah. It has kind of a nice symmetric distribution of these houses. So it might be that the reflections that are coming from the house are all coming with the same power. And then same power, different phase, gets close to Clark's model, and there's 4 of them. Maybe if I were to have 6 or 7, that's typically sufficient to simulate Rayleigh fading. That would probably push it, the power fluctuations, more than 10 dB. And yeah, all these 3 slides that you've seen now are summarized here. So this is that particular non-line of sight tree which shows the most diverse. And indeed, the power fluctuates the most, and it also fluctuates the most in the middle, where the receiver is the most likely to be.
So when you did your how the channel, the shape of the channel, right, even for line of sight, right?
Mm-hmm.
And then you sort of took at the distance of you looked at the correlation at some distance, let's say a few centimeters, or 10 centimeters, or 20 centimeters.
Yeah, the scale is not the same. This is, I think, 16 meter, and this is 2 meter.
But I'm trying to sort of figure out in that scale over there, right, in the line of sight scale, you do get a change of 5 dB within 10 centimeters.
Roughly. This is half a meter. So you get 5 dB in 25. Less, maybe 3 or 4 dB in 25 centimeters.
I'm looking even line of sight. You know,
Yeah.
red line, the left.
So this is one direction. This is the other direction. Don't get confused by that.
Direction. So which one is more significant, direction of travel or?
Well, because this one is compressed, it's hard to say. Because it does not correspond. This is 16 meter and this is 2 meter, but I didn't have any other way to plot it. How would I?
So what I'm saying is, like, in line of sight, you get high correlation at 10 centimeters.
Yeah.
On the other hand, the power seems to be different by 4 dB.
Yeah, roughly.
So it's the change. H has same shape, but it's down by.
Right.
So can you conclude that?
Yeah.
So what do you think that?
I guess 4 dB is not.
If you look at the shape of the blue one, like, and you take a distance 20 centimeters.
Right.
You know that?
Yeah.
So
Let's say
all
like
across.
this, 25 centimeter, and if you map, you roughly get maybe 3-4 dB change.
4 dB change. Okay. But based on his curves, right? He gets very similar H's here. So his correlation is within 0.8.
Ah, okay, you're trying to get consistency of time versus space.
Well, I'm also trying to find consistency between H's and powers. It looks like the 20 centimeters, even though the shape is similar, the total power is 4 dB down, which is significant.
He basically believes that, if I can try to interpret, that if you see 4 dB, you should get change, you should get correlation coefficient less than 0.8.
Well, I'm not necessarily claiming that. I'm just saying that how do you study diversity, right? Maybe H changes, right? But the power is 4 dB different. So even though my H is the same at these 2 points, let's say it is the same, right? Or very similar. But the power is 4
Well,
dB
there's
different.
actually
But you
three
said
ways to
power is
look
not
at it.
common. It's as if on this plot now I'm following what you're saying. It's as if Harris parked one antenna at one dip of the curve and another antenna at the peak, and would have said that they are somewhat uncorrelated at 20 centimeters.
The power is different.
Right, but it's not a common power. It's the instantaneous observation here, right?
Yes, but that's the point, right? I mean, in some sense, you can sort of like look at the previous results and claim, well, the H's are same at these 2 points. But then you look at this slide and you realize that the power is by 4 dB different. And you can sort of go back and conclude that you really need 2 antennas because you don't know which one is better by 4 dB than the other. Even though
you subtracted the mean.
Yeah. And the other one, he subtracted the mean.
Yeah.
Was this the scale of mean calculation. I thought it was like a meter or something.
Yeah.
Oh, so that's not a problem because the mean was smeared across. The mean did not include. I mean, it smoothed out the variations you see here. I mean, that's what I mean. Because the mean was calculated over a meter.
You subtracted the mean to compute the power?
To compute the
No,
correlation.
not for the power.
To compute the correlation.
Correlation, yeah. But the power is there.
Yeah, the power is the power.
Yeah, but, right, so based on the previous argument, right, that we discussed, you take two antennas at 20 centimeters, so the H's are very close to each other, right? I'm not saying it's a problem, I'm just saying that the conclusion sounds like, our conclusion should be that there is no diversity because H doesn't change, right?
Yeah.
But the power seems to be quite different.
I think you're right. The implicit assumption when you look at correlation coefficients is that the average power is the same.
Right.
So when it's not, like in the blue curve on the right, then you have to take that additional factor into account in estimating how performance is going to be.
Yeah, that's all I'm saying. And this is an additional curve to those curves.
Yeah.
In
Right.
a different dimension.
You're right. When there isn't much of a power difference, then you can just look at the correlation coefficient and draw some inferences about diversity.
Right.
But you're right, when the power average is basically different, then that's an additional factor in evaluating.
Yeah, the only problem I have with that is that you have to move by, say, 3 meters to see it.
Yeah, right.
Even if you're driving, let's say,
Depends on what you look at.
But wouldn't the average power, I mean, when you do the expected value in the calculation, isn't that the value that you get by drawing a line through the middle of the blue curve?
Yeah. You mean, do these two correspond?
Oh, I was looking at I was concentrating on the transversal, the one on the right.
Yeah, they better be. I put the 0
No,
here.
that's not what I was checking.
And I think that's pretty much it. So what we did, we basically introduced reflector tiling to deal with the short-range propagation. We modeled channel transfer function as the superposition of the reflections from the tiles. We used the simple physical optics RCS model to do that, and then we verified this simple model we verified this model experimentally. And then in the second stage, we applied the timing model to slightly more challenging environment. We performed a numerical analysis of 2-lane residential road, and Larry's great idea of splitting the receiver area into contiguous squares really helped because it provided quasi-stationarity inside the squares. And basically all this work points out that on the average inter-antenna correlation is larger than 0.5, which means it's not a very diverse channel, and if you convert that to time domain, that would correspond to a very slow fading channel on the order of hundreds of milliseconds, so you can send multiple packets and the channel is not going to change in that period. So it's interesting, if anyone is to ask me, so what's the original contribution? I kind of wonder, because if I look at historically what people did before, the experiments I did are very similar. I mean, the issue I consider is very similar. It's a different environment, and I borrowed a lot of ideas from this Lee's paper from I think 1973, where he was addressing the problem of how much should I separate antennas on a base station to achieve diversity. And the way he did it, for instance, they did measurements on 6 routes, which kind of corresponds to 8 geometries. That's nice. singularity. Then going back to the issues of radar, the first organized, the first structured experiment with the radar was basically to determine how the radio signal fades. It was not actually the radar problem, but rather perturbation of the channel which messes up with the communication. So apparently there's a duality between the radar and the communications problems. The common theme, which is nicely exposed in Van Trees Volume 3, is that there's in both cases there's the same underlying component, which is the channel. In one situation, the moving target perturbs the channel, and then you send a known signal, and from that change in that known signal, you're trying to figure out where the target is. In communications, the channel perturbs, and then you're trying to guess unknown signals because they're first unknown at this because they're coming from the source, and then in addition the channel perturbs. So that's it. So this kind of is supposed to illustrate that on Manhattan, when you're 1 meter apart, you cannot achieve diversity. So which agrees with my conclusions.